Hello, Dr. Ron England here, and we're getting towards the end. Module 14 of 15, and this is kind of getting really 14 as the culmination of everything we've done, because we're going to talk about Anova. And the reason Anova is important is because it really is the technique that you use heavily in the design of experiments. And the core concept is actually relatively straightforward. You design an experiment, and I'm going to talk about it one way Anova here, but we design an experiment and we've got multiple groups of data that we've collected on multiple conditions. And we really just want to know if the means are statistically, are they different or are they the same? And it's a comparison of variance, and you can determine if there's specific group differences in your experimental design. Now, it's going to make a lot more sense when I actually go over some samples, some examples, and I'm going to give you kind of one example that I'm not going to calculate, then an example of one that I've done that I am going to calculate. So the one way Anova is means across groups. So let's say you got 3 samples, and you want to know the null hypothesis would simply be, are the means equal? And the alternative hypothesis would be, is one different? And that uses the F statistic, and we're going to do a sample of that, which will make it a lot more clear. But that's the basics of the one-way Anova. So what do you do in the calculation? You take the 3 different groups, you calculate the mean of the values in one group, of each of the groups, calculate the total mean, then you compute the sum of squares between the groups and within the groups. And that actually gives you the ability to calculate the F statistic. And the F statistic can be compared against the critical F statistic to determine whether or not you reject the null hypothesis. So to do the critical F statistic, you've got to know the degrees of freedom. And there's basically 2 measured degrees of freedom that you've got to look at. Degree of freedom 1 and degree of freedom 2 is what they're called. And the first degree of freedom is the number of groups minus 1. And the second degree of freedom is the number of measured samples minus the number of groups. And that actually gives you, at any significance level, the ability to calculate the F statistic. And then that F statistic is then compared against the critical F statistic. And if the F statistic is greater than the critical F statistic, you reject the null hypothesis that all the means are equal. You can do the same thing with the P statistic. The P statistic actually represents the probability of observing an F statistic when the null hypothesis is true. So essentially, a low P value basically means that you would reject the null hypothesis. A high P value means that you would not. Low probability of rejecting of observing the F. I'm going to confuse you. If the P is low, very, very low, you are going to reject the null hypothesis. So rather than looking at the formal definition, we're just going to stick with that, because every time I try to state it, I'm realizing that I'm just making it more confusing. Now, there's a bunch of assumptions, and the normal assumptions that we typically make: the independence of variables, and normality, homogeneity of the variance. Basically, you're saying, okay, you're taking good samples that are representative of the group that you are putting those samples in. We do have a number of diagnostic tools to know if those samples are good, things that you can actually do, that you can use to calculate whether your assumptions are decent. Now, there are other ways to go ahead, and there are other ways to actually look at the visualization of the samples to determine this. Or you've also got the ability to modify the models. And we talked about that literally in 13 when we looked at variable transformations. We are not going to do variable transformations with Anova. It gets really complicated once you start going down that road. I want you to be able to do a standard one-way Anova and be able to translate the results. I think from that, you're going to have the capability of dealing with all the other ones. And I am going to cover it in a little bit, but we're not going to actually do it. So when you're doing a one-way ANOVA and we're looking at multiple samples and we're saying is the mean of 1 equal to the mean of 2 equal to the mean of 3 equal to the mean of 4 with 4 different samples, well, you might get a specific situation where you reject the null hypothesis, meaning that no, they're not equal, but the reality is that they may be that 1, 2, and 3 are equal and 4 is off. And in that case, you've actually got to look to find out which one of them is not, which one of them violates that, causes the violation of the null hypothesis. So you may actually have that only one of the samples is not equal to the samples of the other means, and there's techniques to do that. And I'm not going to go into the detail of that either, but I am going to cover, really you're not going to do this, but there is a way to do this. Tukey's honestly significant differences, where you're actually looking at the mean differences and then individual critical values and looking at specifically if, and what it is, it's a comparison of groups. It's A to B, let's say you got 3. It's A to B, A to C, and B to C. If you had 3 groups, A, B, and C. Okay, so you're comparing A to B. That's one of the comparisons. A to B, A to B, A to C, and B to C. And there's only 3 of them in that specific scenario. As soon as you get into 4 groups, there's it tends to get very large very fast when you're actually doing those. So oftentimes you'll do calculations with 3 or maybe a maximum of 4, but it's capable of doing more. You can do more than 4. And if you're actually having the computer do the calculation of the honestly significant difference, then it really doesn't matter how many groups you have. It really just then gets into the translation of the results. And I'm going to show you that translation of the results for a one-way ANOVA, so that you'll be very glad that I'm not making you do it for the for a two-way or looking at the individual samples that cause differences. So, what are the calculations do you have? Bonferroni correction, Sheffy's method, and the Donet's test, which are just other specific comparison methods that you can do. Again, not covering them. The reason that they're here mentioned is because I want you to be aware that there are other methods. That's it. That's what I want. Now, two-way ANOVA. And this is where you're actually you're looking at multiple factors. If you have a factor that causes an effect and another factor that causes an effect, what you've got to do is you've got to look at the interaction. So in the example kind of gives this. The overall effect of fertilizer type on crop yield, and then factor B would be the overall effect of irrigation method on crop yield. Now you've got organic, chemical, drip, and sprinkler. So you've got 2 different things that actually have multiple factors of effects. And that means that you could actually have an interaction effect where the fertilizer performance is actually going to differ based on a specific irrigation method. And in that case, you've actually got to do the two-way ANOVA to look at those interacting effects. I, again, want to know that you know that this can be done. We're not doing two-way ANOVAs. I mean, the framework is this. You're looking at the factors and the interaction effects that go with this. And then it's just a partitioning of the sum squared of errors. Again, not getting into details, but if any individual student wants to go into or has a scenario where they're going to actually need to do two-way ANOVA, then I will put something out to the side for them to be, I'll actually create them a nice little two-way ANOVA video so that I can show them how that works. But it really is getting into graduate level work when we do this stuff. What we're doing here is this is a visualization technique for looking at two-way ANOVAs, and what it does is it actually gives you you can see the lines in parallel lines when you've actually got interaction plots, that's just a specific plot type, and if they're parallel, there's no interaction. But what happens is you can have them actually cross, and that does indicate that there's an interaction effect. So I'm kind of moving through this because I want to get to the example here. And then visualizing And looking at most of the visualization of ANOVA results, what I'm going to have you do is the box plot really gives you most of what you need to do. Now, if you're doing two-way ANOVAs, you've got to go beyond the box plot because it's not going to show you any of the interaction effects that you have to take into account. So an interaction plot would be necessary if you're doing a two-way ANOVA. And again, just remember the two-way ANOVA is looking at an experimental design where there's potential of interaction of one with the other. All right. Looking at the effect size, there are a number of statistics that you can calculate, and there's only one that sits inside the regular ANOVA results, which is the partial eta squared, which is the middle one there. But what these mean is what portion of the variance is explained by what. So in the eta squared, the total variance is explained by a factor or an interaction. It's actually the proportion, the proportion of the variance, which is explained by that. And that eta squared gives you a measure of that. That and the partial eta squared would be the ones that you'd be most likely to use in regular work. And in the partial eta squared, it's looking at the variance explained by a factor after you exclude the other factors. So you move those off to the side, and that's what it gives you. Now, I'm going to show you where that, in my example, I'm going to show you where you actually get that value, but we're really not going to go into the detail work of how that happens, because we're going to concentrate on that one-way ANOVA, which is the one that I do want you to be able to do. Now, this is used in quality control heavily, because in any of the things where you're doing the monitoring of individual processes to outcomes or looking for defects in a manufacturing process, that you're going to have multiple samples that you've got to compare that are underneath different conditions. And when we talk about different conditions in manufacturing process, we really talk about temperature in the room, the operating shift, the equipment being used, or how long has it been since a maintenance cycle. There's so many different things that you can use the things that you need to measure to understand how to optimize quality control. And they all can be measured to see if there's any significant difference between what is going on using an ANOVA. So how do you do it? It's actually quite simple. You design the experiment to measure what it is that you want to measure. You run the processes, and then you analyze it with an ANOVA. You look at the ANOVA results, and then you can use that to optimize the settings. It's really not much more than that. Again, much easier demonstrated when you get to look at an example of it. And there's different types of what we call factorial designs. This is actually getting a little bit into how do you make up that experimental design. And I'm going to mention these, like full factorial, which tests every possible combination of the different factors. Fractional, which tests a subset. Or randomized, which controls for something that's a known. There's what's called a hierarchical randomized structure that you can do, which is called a split plot. And that's about as deep as you're going to get, because I've never done a response surface. But it maps, I know what it does, but I've never done it. It maps, there's a relationship between the factors and the responses, and it actually tries to get what that relationship is. But it does exist. And maybe someday I will do one, but it's just never come up. Other than inside of a class, because I did take, when I was doing these in classes, but I'd like to see a real scenario where I actually use it. Another one is you can measure the same thing at different times or different conditions and actually repeat the ANOVA underneath a different set of conditions. That's an interesting application also. And again, outside of the one-way ANOVA scenario and the two-way ANOVA scenario, this gets into how to do the experimental design. So I'm kind of leading to where I want to go with my example. So guess what? Well, first, I'm going to cover the foundation of a one-way ANOVA with an example that I want you to be able to do. Now, as you get into the number 2, where you actually look at how to do experimental design, if you're going to be in the scenario where you're actually going to do experimental design, this is if you're going in any type of research, you do need to come up with different types of experimental design. So that becomes important. And you need to understand what experimental designs that you can do and how you can do, but most important, you need to know, if you're doing this, how you can analyze the results of the experimental design, because that affects how the experimental design looks. And it's used quite a bit. ANOVA is a big deal, and it is used all over the place. And I'm going to give you, when I give you an example, you'll get to see this. And then there's actually more advanced, because you can get beyond ANOVA into multiple ANOVA, which is MANOVA. And then also non-parametric alternatives, which is well beyond what we would do in this class. But I want you to know that we're not at the end point. Now let's give an example that was one that I did. Now I didn't use the data from my experimental design, but one of the things I had tasked with is looking at whether you have differences in different teaching methods. And these teaching methods will be very, very familiar to you. Purely live classes, hybrid online and live, and fully online classes. And that is relatively easy to measure. Now, now talking about the experimental design of this. First, the classes had to have the same outcomes, same materials, the same lectures, and the same exams, and the same homeworks. All those factors had to be controlled for this. And this was done, I'm not going to say it was done in an algebra class, because it wasn't. It was actually done in mathematics, and it was used to determine the applicability of prerequisites based on the different styles of learning. It was part of a larger project that I did, but this is a great example. Now, I did kind of play with the data a little bit so that it came out nice and easy. So what are you doing? You've got three methods that you're doing. The levels, and we're going to call them A, B, and C, are live, hybrid, and online. The dependent variable was the final exam score. Okay, it's a continuous variable. We didn't use the grade, we used the final exam score. And the reason we didn't use the grade was because there's so many factors that affect the overall grade beyond this that is not a good control variable. It seems like it would be, but reality is it's not. But the final exam score is, and there are ways to test whether that's good, which we didn't do. So there's 3 groups. Null hypothesis is that the mean of A, live, and the mean of B, hybrid, and the mean of C, online, are the same. And the alternate hypothesis is that they aren't. All right, so first, I'm going to show you the ways to do this. Now, there is a library in Python called Penguin. It is really handy, Penguin, and you might have to install it if you don't have, and it's easy. If you try to put it into an import in Colab and it says it isn't there, it'll say, do you want me to install it? And it'll let you install it, and then you can use it. So Pandas, Penguin, Seaborn, and Matplotlib, but Seaborn's got some really nice graphics that you can do. I mean, the visualizations, and I can't even remember if I used Seaborn in this, but I did put all those in there. So the first thing I did is I want to put everything into a data frame. And once you get good at data frames, the nice thing is the AI can help you. If you tell an AI what kind of data and what kind of experiment you have, it can often create that data frame code for you very easily, because it sometimes is really a pain to do. But you've got 2 things here, the methods and the scores. The methods are the 3 different methods, live, hybrid, and online, and the scores are the values that went with it. And notice I put comments in, and I always comment the crap out of my code. And first thing I do is I put that data into a data frame. So I basically take the data using Pandas, convert it into a data frame, and then I printed it just to check sure that it was okay. It was fine. it was in the form. So basically, I've got 3 groups of scores, and that's what I would want to see in. And if you print a data frame, it just gives you a big long list of everything with all the different columns that are associated with it. Now, the next thing that you want to do is you actually want to do the Anova, which is really one line of code. But you got to give it some information. So using Penguin, which is I think is the easiest way to do an Anova, because it's just a simple command Anova. You give it the data, which is the data frame, and the data has to be in a specific way where you've got the different test groups in their own individual columns. And then the column that we're gonna be using the score for the data, and the between is going to be the different methods. There's 3 different methods, and I said to put the output I want is a detailed output. And what you get is an Anova table. So this bottom thing here is an Anova table. Now I'm going to actually kind of give you an idea of what that is, because if you look at this, you're like, oh God, look at this. There's a whole bunch of numbers and abbreviations. But here's what it means. Once you see this, it's not that really difficult to do. I'm going to move my face down to here so you can see what this is. So the first one is when you're doing an Anova, you're looking at the variances between the methods and the variances within the methods. So there's within a method. So look, when you look, so you think about this. If you've got a set of data, I'm going to go back to here. If you've got a set of data like live, it's got some scores, and there's variance between the values in the method. Okay. And that is important. If there's massive variance there, then it's going to be a big, wide, the confidence interval is going to be big. So, but the way the Anova works is it first looks at the variance between the methods and then the variance within the methods. So the variance between the methods is k minus 1. K is the number of methods, and that should make perfect sense that the degree of freedoms is 2, because k is 3, and degree of freedom is usually n minus 1, so that's 2. And then there's the means of squares, but most important thing here that we're going to use for our comparison is, so you've got some squares and mean squares, but then you've also got the F statistic and the uncorrected P. There, when you're doing a complex, I'm not going to go into that. I'm just going to leave it there. The uncorrected p-value, but the uncorrected p-value does have the ability to be compared. And then the partial eta squared effect size, which we aren't going to get into. Then within, you have the same thing, the sum squares. Now, the degree of freedoms of the within should be the number of points minus the k, which is the 3 from before, and that should be 45 minus 3, which is 42. And then it doesn't actually have an F statistic that works because, well, and it doesn't make any sense that, well, it could make sense, but for because you're looking at multiple, okay, well, let's just go with that. There's more than one sample of within. So there's not one F statistic. Okay. Now, we said, and I don't know, I'm hopefully not losing it. We said that we got to compare the F statistic against the critical F statistic. But just the p-value alone, e to the minus 20, should kind of tell you that you're probably going to reject the null hypothesis. That's a pretty low number. Now, we do need to calculate the critical F to do the comparison of the F statistic too. So we have the degrees of freedom, DF, which are, by the way, you can just pull right off of that, but it's 3 minus 1 or 2, and then 3 times 15 minus 3, which is the 42. Degree of freedom 1, degree of freedom 2. The critical F statistic is then you're going to take the 1 minus alpha. The alpha is going to be 0.05, so we're looking at 0.95 for our for the actual that big value, but the alpha value is 0.05 because you always use 1 minus. And the critical F comes out to be 3.2199. I think 3.2 is close enough for this. And if you look at that, you can now draw the conclusion that you want to do, because you've got the critical F and you've got the F of the between, remember, the between the methods, which is 159. Now, I'm going to go ahead and throw up a visualization to show that this actually does make sense. So the F statistic between the different methods was 159. The critical is 3.2. The F between is greater than the critical. And we're going to reject the null hypothesis. There is definitely a statistical difference between the samples. And then the same thing with the p-value. A typical comparison of a p might be 0.05. This is 2.5 times 10 to the minus 20. It's actually a way, way, way small. So, and then I'm just going to, remember I said the box plot is a really good way to do a visualization of the three. In fact, it's probably just a good idea to do a box plot before you even start. I mean, from this box plot, I could have just said right off the bat, those are completely different. I mean, you could do it by looking at the data or even just comparing the means. But remember, if you're only comparing the means, you're really not looking at, I mean, one of these samples could have had a massive variance in here. They didn't, between the individual values that were in the sample, but they didn't. I did kind of, the reason this looks so pretty is because I cleaned up the data. So I did introduce some bias into the samples, but I introduced the bias just for the demonstration purposes because the real analysis was not quite as cut and dried as this. But what do you need to know what to do? Okay, what do you need to know and what do you need to know what to do? Because that's really what's going to be important because we're kind of getting down to the end here. Now, understanding, I'll tell you what, I'll give you a nice review in lecture 15 of the important pieces from this class because there are things that you do need to know how to do to be good. And then there's things that you may do in the future that you're going to actually prep for. This one is, I mean, I don't know. I'm only going from my own experience that Anova is something that for me you'd be likely to do because I do look at experimental designs and try to determine if something actually has an effect. But there you go. Nice little conclusion there with the box plot. And I think this is an example that most everybody would understand. If you desire for me to do an analysis with an example of a two-way ANOVA, I will be happy to do it. You just got to ask me, and it'll be 14B, or I'll make it because it's module 14. Module 15 is already kind of done, so I don't want to go into what, I don't want to use that number, but I'll be happy to do it. You just got to ask. And I will continue on because I think the example is the best demonstration of what this is. I will not be going into all of the more, well, I'll call them obscure, but the more obscure factors. So that's it. Whew, 27 minutes, yes.